We got example time. You know, I love my examples because I think they're good for you. In the long run, I really do think they are good for you. The more of these example problems that you can do, the more comfortable that you feel with organic. The problem, again, I'm going to say it over and over, is that people do not do examples in organic. And when that happens, all of a sudden they get a test and it's like a foreign language and they don't know what to do. All right, so here are 6 more examples that we're going to meddle through and figure out if we can answer these questions or not. So this problem says, what would be the major product obtained from the addition of HBr to each of the following compounds? So we're going to be using Markovnikov's rule. We're going to be using this concept of regioselectivity. We're going to be using carbocation stability in order to answer these questions. And this is how I answer them. So they work for me, and maybe it works for you too. We'll see. All right, so part A. Part A, I'm looking at this double bond, and I know that that double bond is going to break, and I'm going to have a side of attachment here and a side of attachment there. All right, so Markovnikov's rule says hydrogens play with other hydrogens. Clicky. All right, so here's the hydrogen, and that comes in first. And it looks at these 2 carbons, and it looks at the one on the left and says, oh, well, hey, you kind of socialize with people that I socialize with, but this carbon's more popular. This carbon over here has more people that I socialize with, so mob mentality here. Bing! That's where it goes. So this turns into a CH3 group right there. That's how we do this, folks. It's as simple as that. All right, and then that bromine is going to come in, and the bromine has no other choice than to go to the left-hand carbon in this example. And there you go. The whole purpose of why that worked, why Markovnikov worked the way that it did, is that on this side, this is a secondary carbon, and on this side, it's a primary carbon. So hydrogen went to the primary carbon first, so the carbocation could form on the more stable secondary carbocation. Folks, that was a full-blown organic description right there for you. And if you could understand that, and if that was not a foreign language to you, you are learning organic. So good for you. All right. So let's look at B down below. So this double bond is going to break, and I see a side of attachment here and a side of attachment there. So HBr is going to come in, and it's going to add to this molecule. So where does it go? Markovnikov's rule is followed. Hydrogen looks at these 2 carbons, and it says, carbon to the right, ew. Carbon to the left, you've got a hydrogen. And I hang out with hydrogens. I get along with those hydrogens. So hydrogen is going to go to the one on the left-hand side. Well, this was a CH. Now it's a CH2. It's just my way of shorthanding it and cleaning this up a little bit. All right? So I'm going to erase that bond. What we have now is a carbocation. Well, here, this was secondary, wasn't it? And then on this side, this is a tertiary. That is why Markovnikov's rule worked. It is setting us up so that way we are picking the right carbocation to put this compound on. So tertiary is way more stable. A positive charge forms on that carbon momentarily, and that allows the bromine to go into that particular carbon and attach. So that is the major product for part B. All right, let's look at part C. Part C is a ring structure. I don't treat these any different. The problem is that they typically leave off the hydrogens. Just like we saw before, they're leaving off the hydrogens again. So if I look at this carbon up here, it's got 1 to the methyl group, 1 to the left, and 2 that kind of go below. So there's a total of 4 bonds right there. This has no hydrogens at all. And then this carbon, it's got 2 that points up, 1 that kind of points down to the left. So there's a total of 3. The 4th one is going to be to a hydrogen that they do not draw. So I'm just going to draw it in there. That way I'll know for sure which carbon this incoming hydrogen is going to go to. All right. Okay, so this double bond is going to break, and I get a side of attachment that opens up here, and I get one that opens up there. So I just do true lines. Hydrogen plays with other hydrogens. It comes in. It sees the carbon to the left. It has none. It sees the carbon to the right. It sees 1. And it says, hey, yeah, Mean Girls. You ever watch that movie? That was a good one, too. Well, these are Mean Girls right here. All right. So those two hydrogens come in. Those two are hydrogens. So, they didn't tell me that the hydrogens were there. Why should I tell them that the hydrogens are there? So I'll just erase all of that to clean this structure up a little bit. This forms a tertiary carbocation that is very stable compared to the secondary that would be down here below. And this allows my bromine to come in at that location. So that's where we put the bromine, and there's the major product. All right, so for D, same story, double bond breaks. Look at this, same rehash over and over and over. That's the wonderful thing about example problems. All right, so two sides of attachment open, one to the left and one to the right. Hydrogen goes in. Which one do you think hydrogen's going to go to? Well, if you told me left hand, you are learning. Look at you, CH3. That is correct, folks. That's where it's going to go. This gives me a tertiary carbocation versus a primary carbocation from the left, and that is where my bromine is going to go in example D. All right, so example E, they're trying to trick me, I think, aren't they? The double bond is not in the ring, it's between the carbon and the ring. So no big deal. This double bond still breaks. I have a site of attachment that opens up at that carbon, and I have a site of attachment that opens up at that carbon. Hydrogen plays with other hydrogens. Which one is it going to go to? Well, I hope you told me the right-hand one. If so, you're learning again. Good for you. Ding, 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 ding. You got it. So there's my CH3. And then to the left-hand side, that is where my bromine is going to go. So there is the major product for part E. And then part F, look, I'm turning you all into organic chemists and you don't even know it. And you might even have fun doing it because you're getting it. And I hope so. I hope that's the story. So for F, here we have a molecule, same deal. Here we get a double bond that's broken, a site of attachment that opens up here, and a site of attachment that opens up there. Hydrogen comes in. Markovnikov's rule follows. Well, to the left, I've got one hydrogen. To the right, I've got one hydrogen too. Huh. Well, this hydrogen's going to say, I don't care. I don't care which one I go to. Whichever one that wants to bring me into their groupie. Okay, so the one to the left and the one to the right, it's actually the same because that carbon has a methyl group and a hydrogen on the left, and the carbon on the right has a methyl group and a hydrogen there as well. So it's identical. I don't get a mixture of products here. It's the same product no matter how I do it. So it doesn't really matter. I can put hydrogen here to the left-hand side and turn this into a CH2, and then if so, that's great. And then on the right-hand side, that is where my bromine is going to go. Now, you might be saying, well, wait a minute. I don't see how they're the exact same product. That doesn't make any sense. Well, let me prove it to you. This double bond is going to break. And then here, let's put my bromine at that location. And then my hydrogen to the right-hand side and to the left-hand side. Now, let's go through and name these. All right, that's the easiest way to do it. I'm telling you that these two are the same structure. You might not believe me, but let's name them. So this is a 1, 2, 3, 4. This is a butane right here. Okay, I number closest to the right-hand side because that's where my bromo group is at. So this is going to be a 2-bromo-butane. All right, so let's name the one down here below. I do the same thing. Longest carbon chain is 4. That's but. And then this time I'm going to number to the left. And the reason is because that's the closest to the bromine. So this is still a 2-bromo-butane. Look at there. It's the same name because it's the same compound. And the nomenclature rules are going to prove it to you. All right? Okay. So folks, if you can do this type of example problem, I will say that you are on a point of a very good experience with this lecture. If these are still problematic for you, then maybe you need to go back, rewatch some of my videos, go into the textbook, read some of that information, and try to practice more of these examples. It's all about this first, and I'm putting so much focus on it in the beginning because it will make our job much, much easier later down the road in this lecture module when we begin to talk about other reactions that involve things other than HBr and HCl and HI. I mean, that's really all that they've given us so far. But there's tons of more of these reactions that we're going to have to learn. But these rules are applied to every one of those that will be coming our way. All right, now let's take a look at a different type of example. These are the ones that people do seem to struggle with, and that's because they're backward. What if we had something that reacted with HBr? And this is what we ended up with. CH3, CH2, CH with a Br that hangs down here, CH2, CH2, CH3. And the question is, what would be used in order to get that product? Now we're talking about really synthesis. This is a synthesis type of problem. Synthesis basically means to make. You learned that in general chemistry. It was one of those 5 classifications. You talked about synthesis and decomposition and single replacement and double replacement. Well, here's the synthesis reaction. How do we make it? That's what that means. I don't really know why people have problems with these, especially in the beginning, because they're going to keep them kind of simple and they're going to be one step and one step only. But the trick here is to really go and look at the best possible route. That's where people mess up. So you're looking at this type of equation and you're thinking, well, this I could maybe try to see. We need something to react with HBr to give me this. And if I look at this product, I see the Br right there. And all of these examples that we've done so far, Br had to be on a sp2 carbon, right? So this carbon was involved in a double bond. The point, though, is that to the left, a double bond could have happened, or to the right, a double bond could have happened. That's where the problem lies. That's where people struggle with sometimes, because they have to make that type of decision. All right, so if I erase that Br that is there, because I know that my double bond has to happen at that location, I'm going to come down here to the bottom. I'm just going to draw these choices, okay? So CH3, CH2, CH, CH2, CH2, CH3. So I'm erasing this Br that was right there at that location. I'm going to get rid of it. I know that a double bond has to happen between that carbon and another carbon. So let's do the one to the left-hand side first. Well, if I do that, HBr was added. I'm going to have to get rid of one of those hydrogens as well. So there is the double bond, and that is a possible reagent that we could have started with right there, right? I mean, think about it. If the double bond is there, the double bond breaks, 2 sides of attachment open up, one to the left and one to the right, and hydrogen plays with other hydrogens. We determine what the products are. But that wasn't the only choice. Some of you could have also said, well, we could have done it right-handed. We could have. So we need to draw that version down as well, right? We need to eliminate some of these choices if they're not very good. So here was my Br. I'm going to go in and I'm going to erase that Br and that bond. And I know a double bond could happen. I did it to the left, but now I need to do it to the right-hand side. All right, so double bond goes to the right-hand side there. Well, if I do that, that carbon, the neighbor, it has to lose one of its hydrogens, right? So it's got to be a CH because, once again, that double bond will break. A side of attachment will open up on each. Hydrogen goes to one side, Br goes to the other. So these are the 2 choices here. Let's name them. 1, 2, 3, 4, 5, and 6. Well, this is the second carbon in. I have the double bond. So this is a 2-hexene. And then here, what I have is a 1, 2, 3, 4, 5, 6. And this is a 3-hexene. So at first glance, it looks like both of these would work. And they do. They both do work. They both give me that product up there. But one of these is going to be much better than the other one. One of them is much better than the other one. Can you figure out which one it is? Well, let's think about geometry here for a minute. I don't want to be wasteful, okay? And I know that reactions could be regioselective, and some reactions are not regioselective. All right, so if HBr gets added into 2-hexene, That double bond's going to break. Two sites of attachment open up. Hydrogen plays with other hydrogen. All right, so the one to the left has a hydrogen. The one to the right has a hydrogen. And it says, well, it just really depends on if it's a Wednesday or a Thursday, which one I want to hang out with. Kind of attitude-ish, isn't it? Shame on that hydrogen for being that way. Okay, well, if that's the case, we get a mixture. We get a mix. All right, and that mix, I'm going to shorthand skeletal structure it here. 1, 2, 3, 4, 5, and 6. All right, so 1, 2, 3, 4, 5, and 6. If this double bond breaks, on that second carbon in, hydrogen's going to go there, and bromine would go here. That's good. This is what we want. Third carbon in, that's where my bromine is at. However, the other choice could have also happened. Makovnikov's rule says that it could, right? There's equivalent carbons there, each one having the same number of hydrogens. So hydrogen could have went here to the right-hand side, and that would have forced bromine to the left-hand side. But this is not the product that I want. This is putting bromine onto that second carbon. Okay, well, the question here is that 2-hexene reacted with HBr. It could give me that. It could. We just drew the structure down here. But there is no rhyme or reason. So this is not regioselective here. I'm going to get a mixture of both. Maybe 50-50 split. Maybe 60-40 split. 70-30 split. I don't know. But I'm going to get both of them. Is that the best option for me? Well, let's take a look at my other choice, the 3-hexene. So over here on the right-hand side, the 3-hexene, well, I'm going to do the same thing. 1, 2, 3, 4, 5, and 6. And then 1, 2, 3, 4, 5, and 6. All right, so there we go. So HBr comes in, and it attacks that double bond, and that double bond will break. Well, that double bond's between carbon 3 and carbon 4, so it's right in there. That's where that double bond's going to be. All right, so that double bond is going to break. I get two sites of attachment that open up. What does Makovnikov's rule say? Makovnikov's rule says carbon to the left has 1, carbon to the right has 1. Doesn't really matter. It just depends on whatever the hydrogen wants to do. Equivalent. Okay, well, let's just put the hydrogen to the left on carbon 3, and that puts this bromine on that 4th carbon in. So bromine goes there. And then let's flip it around and do it the other way, because it could have both choices, and that's fine with it. So this time, let's put the hydrogen on the right-hand side, which is carbon number 4. And then let's put the bromine to the left-hand side. Kind of like what we did over here. Well, if you look at this, 1, 2, 3, 4, 5, 6, carbon's on the third, or bromine is on that 3rd carbon in. This is the product that we want. So 3-hexene gives it to us too. And then you're looking at this one and you're going 1, 2, 3, 4. That bromine's 4 carbons in. No, sorry, it can't be. Sorry, you're wrong. You got to be clever. Because if I asked you to name that compound, how would you do it? You would look at this compound and say bromine is over here to the right-hand side. It's closest to the right-hand side, not the left-hand side. This would be carbon 1. This is carbon 2. And look at there. There's carbon 3. So this is a 3-bromine as well. I would name this the same, wouldn't I? 1, 2, 3, 4, 5, 6. 3-bromohexane. This one, 1, 2, 3, 4, 5, 6. 3-bromohexane. And this product that we want up here, 1, 2, 3, bromo, 4, 5, 6, hexane. So 3-hexene is actually a more symmetrical molecule in which the Makovnikov addition, no matter how it happens, gives me an acceptable product if the bromine gets added on the right-hand carbon, or an acceptable product if it adds on to the left-hand carbon. Both of these are equivalent. They are equal. I do not get a mix of products that happen here. It's the same product no matter what. And because of that, this is my better choice out of those two. Now, sometimes that won't happen. Okay, sometimes the version that I write to the left is going to be the same as the version that I get on the right-hand side. One is no better than the other one, and all of those answers are fair game. That's the problem with organic. Not on your end, though, on my end, because I have to take all of that in consideration when I grade your papers. Can you imagine? The longer we go in this class, the more examples, the more routes that could be presented. And you could give me a route that is perfectly acceptable, and I have to count it correct. And somebody else could give me a completely different route with completely different reagents and starting products, but yet they can get to that same product as well, and I have to count that correct as well. So the freedom of being able to choose what you need to choose, that's on your end, and that's a very good thing for you. But on my end, I have to take all of that into consideration. And it makes grading these assignments very difficult and very long. Yeah, I know. Shame on me. What did I do? All right, so here's the example of a synthesis problem that shows you maybe some insight of where this lecture is going to go. I don't know if you feel it or not, right? But if you're feeling that these examples are becoming more complicated, they are. And they maybe quickly will become more complicated, and you got to get ready for them. All right? So this is one example of a synthesis. We will see more of these examples later on. And again, keep in mind, we're only working with one type of reaction right now. And there's going to be more in our Batman utility belt of organic chemistry a little bit later on.